Our next speaker is Andreas Bastian, who's going to talk about the technology.
Alrighty, so my name is Andreas Bastian. I'm a 3D printing research scientist over at Autodesk, based in San Francisco. So, as John said, what e-NABLE is doing and what we're able to do and why we're able to do it now. One of the tremendously important parts of this is the technology that we're using, this 3D printing technology. So, I'm going to talk a little bit about how that technology works, what its current capabilities are, and where we're going to be able to go soon. So, my background's in 3D printing research and development. I used to work at MakerBot in R&D. Since I've done some additional research in bioprinting, tissue engineering in academia. And again, now I'm at Autodesk looking into a variety of emerging technologies and also studying existing technologies so that we can build better software to drive them. So we're going to talk about the basics of the technology, what it can do, what it can't do, and there's some really exciting things coming down the pipe. So the main technology that e-NABLE uses something called FDM or FFF. So that stands for Fused Deposition Modeling or Fused Filament Fabrication. So this is actually a really old technology. Like actually most 3D printing technologies, most of these have emerged in the early 90s or late 80s. So it's actually a pretty well-established technology. It's only just within the past 7 to 10 years that we've been seeing low-cost machines like the Ultimaker that are available for kind of small businesses, individuals, consumers. So there's been a lot of very interesting development done to kind of bring that cost of technology down. These machines used to cost upwards of $50,000, just like the devices that we're talking about today. And so now we can really bring this incredibly powerful technology onto a desktop package. So the way this technology works is it's basically, as John said, a very precise hot glue gun. That hot glue gun moves around in 2 dimensions, depositing a very thin bead of plastic. To kind of conceptualize it, we're talking about a kind of a hair of plastic that's about the same dimensions as the whorls on your fingertips. So making things with kind of fingertip resolution. You can print in a variety of materials. We use a lot of kind of existing engineering materials that are popular for much kind of industry backbone processes like injection molding. The machines are, unlike a lot of the other emerging 3D printing technologies like SLA, are often quite affordable to own, operate, and to purchase in the first place. And again, relative to a lot of the other technologies, they're quite fast. They're not instant. Often you do run jobs overnight, but it's significantly faster than a lot of the other technologies that use, say, powerful lasers, powders, things like that. And so what that looks like in operation, if we speed that process up, just drawing these incredibly thin pictures in plastic, one on top of the other, if you just change those pictures slightly as you go, you can describe an entire object. You can describe a much more complicated object than you could with just a single 2D picture. So what the machine is doing, to take a look at part of the new Raptor hand that we've released, the machine, the software that drives the machine, separates that object, that cohesive object, into a series of layers. And so we're seeing here, as we kind of scale through this object up and down, so we're seeing the kind of what we call the tool path, where that little hot glue gun moves. So this is the drawing. These are the series of drawings that the machine does to build that object up. So 3D printing has a lot of interesting capabilities when compared to traditional manufacturing processes. Most of how we make things is a subtractive process. So you can think about it as like whittling on a piece of wood. You're always removing material. So if you want to make something that has an internal structure, you're kind of out of luck. If you want to make something that has interlocking pieces, if you want to, one of the kind of old Appalachian traditions, whittling a chain, it's incredibly challenging to do with traditional means. But one of the really cool things about 3D printing is it's not a problem to do these extremely complex geometries to make interlocking parts to give objects internal structures. So one of the important things that we leverage a bit and that is going to become more important as this technology moves forward is you could control the internal structure of the object that you're building, which is a kind of a layer of control that we as human designers have never really had before. So you can see, generally, with current software, you can control how much, the density of what we call the infill on the object that you're printing. Anywhere from completely hollow, so just a hollow empty shell of an object, all the way to fully dense, 100% filled. And there's a large gradient in between. And so generally we opt for something kind of in the middle of the road just to give these objects some structural robustness. But there are a lot of interesting things that you can do when you have this level of control. You can control the center of mass, you can move material around inside so that you have more material in some regions. Say if you're going to have a lot of wear, a lot of impact, you can kind of thicken that region up, make it more robust while still maintaining a really high material efficiency. Another extremely exciting thing about this technology is people often say that complexity is free with 3D printing. And while there's a slight caveat, usually you pay for it in time. When you're running prints overnight, or when you're not involved in actually operating that machine, it is essentially free. So the machine doesn't care whether you're making a Lego, a cinder block, or a full engine block. It really will kind of take whatever you throw at it and make it. So there's this really amazing ability to embed an extreme amount of functionality into the design, and because if you make the design more functional, nobody has to come through with kind of subsequent operations and remove material, add material. If you can optimize that design, things become extremely shareable. One of the very exciting things is you can print things fully assembled. So this is one of the really kind of popular objects for explaining that. So like I mentioned earlier, the links of a chain, you can print geometries that have interconnected features. So you can print chain, you can print chain mail, you can print these kind of toys like this. One of the things we've been experimenting with is also printing hands that are fully assembled, so that all of the joints, all of the pieces print fully assembled, so there's no need for assembly. One of the most exciting things, now that these machines are becoming pretty widely manufactured, very easy to order on the internet, you can get them in 24 hours from Amazon now, is the kind of distributed nature of this now. We're seeing, this is an image from a group called 3D Hubs, who has been growing extremely quickly. They basically let you share time on your machine, basically let you share your machine with other people. They have a little over 7,000 people in their network, and they recently calculated that with those 7,000 machines, they have a machine within 10 miles of 1 billion people. So the reach of this technology is spectacular. And especially when you're not actually mailing material, when you're just emailing a file, it almost becomes teleportation. So, as powerful as the technology is right now, we're in a very kind of transient period in this technology. It's been relatively static for about the past 20 years. The last 7 or so years have seen a lot of advances in just bringing the cost of the technology down. And now that there are more people interacting with that technology, working with it, we're making some serious advances. So one of the kind of most exciting things is developments in materials. We can start to kind of have designer engineered materials engineered for very specific performance. So in medical applications, we can start to make materials that have antimicrobially functionalized surfaces that have more biologically functionalized surfaces for tissue grafting, things like that. Additionally, we're getting into some really exciting territory in bioprinting. So it's probably going to start with tissue grafts, small pieces, kind of patches, repairs. But we're getting closer. Within several decades, we will be printing definitely parts of organs, and possibly soon after that, entire organs. So applying this paradigm of just adding material, it opens up a huge amount that we can do with that. Additionally, the way that we structure that material, we're entering this kind of very interesting period where we have the ability to, with this new technology, describe the structure of the material on an unprecedented level. And what that has let us do is kind of evolve these unseen in nature mechanical properties. So this is a microtruss lattice from a group at Caltech. And it's a ceramic lattice, but they're actually able to get very elastic, kind of spongy behavior out of it. So taking a traditionally extremely brittle material and getting these very kind of rubbery, elastic properties out of it. So as we kind of develop the ability to structure material more precisely, we're going to be able to get extremely high performance materials for very specific applications. One of the most exciting things is all of our design tools as a design population, as an engineering population, are entirely based on our previous manufacturing paradigm. When you sit down and open up some of the common solid body modeling tools, things like SolidWorks, Inventor, Pro, CATIA, when you sit down to make a new part, you make a block and then you cut a hole in the block. Because the way you're going to be making that is likely on a piece of subtractive CNC machinery. So we really need to, in order to kind of get the most out of this technology, we need to develop, in addition to new materials, new structural paradigms, we need to develop new design paradigms, new ways of describing what we want to design. Some of the really exciting work going on with this is there's a lot, now that we can kind of describe structures as complex as biological structures, describe bones with porous interior structure. There's a lot of work trying to figure out how to design things and processes that mirror how nature develops these things. There's a lot of work also in replacing a lot of kind of traditional pin joint mechanisms with compliant mechanisms. So again, leveraging material properties to get new functionality. And finally, what we're seeing here on the right, this is a visualization of some experimental software that's being developed at Autodesk that uses kind of computational and algorithmic design strategies to literally evolve these extremely complex, seemingly biological structures to satisfy very specific conditions. So this is actually a bracket for supporting a thruster on a moon lander, where we're optimizing for weight and strength. But we're going to see more processes like this where you as the designer kind of tell the machine what you want to do, and it becomes more of a collaboration with algorithms. So there's a lot of extremely exciting kind of synergistic technology development in addition to the 3D printing technology. There are a lot of systems having to do with distributing the technology, networking the technology, and then controlling what we feed to that technology, what we design, which is some really exciting stuff. So, are we doing questions? Are we jumping right? Okay. Well, then I'll conclude. All right, we can do questions later.